Hello everyone! In this video we're going to be talking about dynamic memory allocation. And this is in contrast to what we've been using so far, which is called static memory allocation. And we'll talk about the differences between the two. In statically allocated memory, every variable that we declare in every function, main and any supplemental functions, the amount of space we need in memory is known at compile time. So every time we declare an integer, the computer knows that it needs to set aside enough space for that integer. And if we declare an array of floats, it knows that it needs to set aside however many size floats there are. So it's going to reserve enough space at compile time for us to store our program. So the memory requirements for all of the data in the program are going to be known ahead of time because they're declared at the top of each function. And every time we run the program, it's going to use up the same amount of space. So if we create, say, an array of 26 float values for a potential 26 miles, like we did in our miles examples back in files, but we only use 7 of them, we're still going to create enough space for 26, even though we're not going to be using all of them. So in statically allocated memory, the program always takes up the same amount of space, even if we don't necessarily use all of it. So of course in dynamically allocated memory that's not the case. The amount of space that we can use for our program changes based on the inputs that we're given. So certain data structures can take up differing amounts of space depending on the inputs. What this means is that the memory requirements cannot be known for sure at compile time. If we stick with the miles example, some runs may use 5 spaces, some may use 7, some may use 10, and some may use 26. And we're never going to know when we start the program exactly how much space we're going to need. The cool thing about that is if we need less space, then we'll actually use less space. So in dynamically allocated memory, we're only going to allocate the space that we actually need. We can use a function to do that, which supports our knowledge of modular programming. We can allocate memory within a function and then make that memory available to other functions like main. The only difficulty is that this dynamically allocated space is not given back to the computer automatically. Instead, especially in the C programming language, it's our job as the programmer to free that memory later. So of course, statically allocated memory doesn't have this problem. The computer knows exactly how many spaces it's set aside through static allocation, and it can free all of those automatically at the end of the program. But if we dynamically allocate space, we have to take on the role of freeing the memory at the end of execution. So we're going to talk about 2 memory allocation functions that accomplish that job. The first is called malloc. It stands for memory allocate. So that's how we're going to allocate our memory in a dynamic fashion. And the other one is free, which is what we're going to use to free that memory when we're done using it. So this is the prototype for the malloc function. The first thing I want to point out is the return type. So this is called a void pointer. And so usually void functions mean that we don't return anything, but that's not the case here. Malloc is going to return a pointer, a memory address. What the void means is that it's unstructured. It's a pointer to memory, but we don't know what's stored there. So anytime we use the malloc function, we're going to have to cast the result to be whatever type of memory space that we need, either an integer pointer or a float pointer or even a structure pointer, to say that's how this memory should be structured. So malloc's going to return a void pointer, which we have to cast. Malloc takes as a parameter some size. And technically this size refers to the number of bytes that we're going to allocate, but we're going to use some special functions to just get the size of the data types that we need. Now in some rare cases, if we don't have space, malloc will return a null pointer to indicate that no space could be found. So it's good practice after we use malloc to check to make sure that our pointer's not null. We actually have space in memory to use. Then when we're done using our data structure, whatever it is, whether it's an integer or an array or a structure or an array of structures, we're going to give that back. We're going to call the free function on our dynamically allocated variable, and it will free up that space in memory. Now this is an actual void function. It does not return anything. We're going to look at a few examples of how to use malloc and free for a couple of different situations. We're going to start out with a really simple version where we just create an integer using the malloc function. So a lot of our interactions now are going to be with pointers. So we're going to create this pointer p, and we want p to store a value. So we're going to first have to allocate space for an integer. So we're going to call malloc. We have to give to it a size. So we're going to call size of integer to say that what we want is something that is the size of an integer. And both of these are, and you can tell since they're blue and bold, are keywords that belong to the compiler. The compiler knows how big an integer is, and it knows that size of is going to return the size of whatever parameter it's given. So now we want p, which is a pointer, so it should contain a memory address. We want it to have the memory address that's returned by the malloc function. Malloc returns a void pointer, so we need to cast that to be the type that we are. So we want this to be an integer pointer. So we're going to cast it to be an integer pointer. And now we are able to use p in that space. So we can go to where p is pointing and put any value there that we would like. We'll print it out, and then before we leave the function, we're going to free our memory. We're done using p, so we're going to give that memory space back to the computer. So that's a really simple example of what we can use malloc and free for. We allocated space for an integer. We stored an integer value there. We printed it out, and then we freed it. And all of this is just happening in memory. We didn't declare any actual integers in our programs, just pointers. So now we're going to do something similar, except we're going to make an array. So I have our numbers file that we've used a couple of different times. It's got 10 randomly generated values in it. And what we're going to do is we're going to read them in and then print them out in reverse order, which is something that we've done in a couple of different variations, so it should be very simple. The new trick is that we're going to not create our array ahead of time. We're going to make our array based on the size in this header number. So it'll be an integer array, so we're going to leave our integer pointer. It's going to be called numbers. And then we're going to also have our header and our file pointer. So we're going to read in that first number from the file and store that in header. And that's going to tell us how many numbers we have. So this one's 10, so that means we have 10 other numbers, which means we should make an array of size 10. So what we're going to do is we're going to allocate space for 10 integers. So we can get the size of an integer using size of int. That'll give us the space for one integer. And then we're going to multiply it by 10, which is stored in header, to say we need 10 integers, enough space for 10 integers. And then malloc is going to go and create space in memory for 10 integers and return a pointer to the beginning of the space that it created. We're going to cast that pointer to be of type integer so that the computer knows that that space is split up into blocks of size integer. Then we can read in the rest of the numbers into this space that we've created. And now that we've allocated space for numbers, we just treat it like any other integer array. We'll read these values into the ith index. And then, of course, to check that that worked out, we're going to print them all back out. And of course, before we exit the program, we've got to give our space back, so we're going to free the space that we previously allocated. So numbers has our allocated space, free numbers at the end of the program. Okay, so what we should see at the moment is the same 10 integers starting after the header value that we've read into our program. And what we want to do real quick is to make this a little bit more modular. We're going to build a couple of functions, print forward and print backwards because we want to be able to see both. And you can see that we're passing in the array of numbers, but we're also passing in length. And that's because we don't know ahead of time how long our array might be. We don't even have a predicted maximal value in our defines. Instead, that value comes from header. So in order to use that in a for loop, we have to pass that along to our functions. So we're going to pass in both the array and the length of the array. So we're just going to print out all of the numbers, and then we'll print a new line at the end. We're printing them out in a row. I'm going to try and get them to line up in our output. And of course, to print them backwards, all we're going to do is start at the end of the array at size -1, which in this case should be length -1. And printing until we get to the beginning, which will be index 0. So we've got our two functions. One's going to print forward, one's going to print backwards. So we should see one the way that they're stored in a file and one in reverse order. And we've got them so that they'll line up. So the first number is here in first order and here in reverse order, and they switch places. So another thing that we can do is do our memory allocation inside of a function, which is really cool. We can increase our modularity by taking the file part out of main and change that to something that gets information from the file and creates our array for us. And it's fundamentally similar to what we're doing here. We're still going to have malloc. We still need to free at the end. The problem is that when we create something in a function, we have to return somehow the pointer to that memory space. If we create the pointer in the function and then don't return it, then we've lost that space that we've created. We not only can't access it, we also can't free it. So if we're going to do that with a function, we have to make sure we return that pointer. So our return type is going to be of integer pointer. We're going to return that space. So we're going to build our function to have some of those pieces that we had in main. And of course, we know that we could ask for the name of the file instead of hard coding it. I'm going with that route because it's a little bit faster and because I only have the one numbers file. We're also updating the length. So we're doing two kind of complicated pointer tasks here. We're going to return the start of our array of integers, but we're also going to update length, which happens to point to header in the main function, so that we always have a consistent length. So we're going to have to get length from the file and then create that much space. So anytime we're using length as an actual integer value, we have to dereference it. So hopefully that makes that a little bit clearer. We have to go to where length is pointing because length is an integer pointer, which means it doesn't store an integer, it stores a memory address. So we have to go to that memory address to get the value 10 so that we can multiply that by the size of integers, so that we can allocate space for 10 integers, so that we can make an array out of it. Then for 10 iterations, I starts at 0, I is less than what length is pointing at, which is 10. We can read in values. To put in our p array at index I. And then we're going to return an integer pointer which is P, which is our numbers array, which is going to be stored here in numbers. So now we'll run it and make sure that it's working. It should look exactly the same as before because the functionality of our program hasn't changed, just where all of the constructs happen. We took them out of main and put them in get values. Since we've been working on structures in our previous chapter, I want to do a few more examples that involve structures. We're going to create some Cartesian points, so points on a Cartesian plane, which we know are composed of an x value and a y value. So we can create pointers of structures just like we can create pointers of any other basic data type. And what this will allow us to do is make a random point just by accessing the random number function. So we'll see the random number generator, and then we can allocate space for our random point, and then we can give it values. This is going to look very similar to where we were allocating space for an integer. The difference is that when we call size of, we want the size of something that is of type struct points. Of course, remember when we call malloc, it's going to return to us a void pointer, so something that is unformatted, which we want to format into something that is a pointer of type struct points. So we're going to make it a struct points pointer and cast it to that type. Now we can add values to our random Cartesian point. And remember, random point is a pointer, so we're going to use the pointer notation for structures. So we can set the x value and the y value to be specific values if we're interested, or a random number. In some range that we think is best, and then that'll be a random point, which we will then print out. Both the x part and the y part. And remember, before we leave, we're going to free our memory. So we're going to free random point before we leave the main function. Okay, so there's our randomly created point. X must be 4, y must be 9, because this is the point 4, 9. On our last example, I want to make an array of random points that we'll print out. So we will have to decide on a size. Let's ask the user for the size. So I called it size. We could also have called it num points. That would make sense. And now when we go to allocate space, we don't want just one thing of struct points. We want size boxes for struct points. So we're going to multiply that by the size of each individual value. And that will make rand point into an array of structures of type struct points. So now instead of having one random point, we have an array, so we have to index our array and set each of those x and y values to be a random value. And when we print them out, we're going to print out all of them, depending on what size it is. So go to each ith random point and print out the x value and the y value in this format. And before we quit, free random points, which is freed the same way because it's the only pointer to a space in memory. So if we free that, it should free everything that was allocated. Now before we run it, we've got to really take a look at our syntax. We have this random point at index I. So I is already indexing the array, and what we find at each individual element is not a pointer. So we need to swap our pointer notation for our dot notation. So random point is a pointer, but random point at index I is not a pointer. These individual elements are not pointers. So now we've made sure our notation is consistent. So when we print it out, it's going to ask how many random points do we want to make. I'm going to make 5 of them, and so we should see 5 random points that we've created. In our next video, we'll continue to explore structures and pointers and memory allocation as we create something called a linked list. I'll see you then.